Sit back, relax, and welcome to Reading Hours. Today's book is A Brief History of Time by Stephen Hawking. Please let us know in the comments from where you are watching, or if there is a book you want us to summarize in future. In the vast expanse of the universe, where time stretches infinitely and space is woven with the fabric of reality, one book has stood as a beacon for those seeking to understand the mysteries of existence. A Brief History of Time, written by the legendary physicist Stephen Hawking, is more than just a scientific treatise. It is a journey through the cosmos, an invitation to explore the fundamental questions that have shaped human curiosity for centuries. How did the universe begin? Does time have an end? What lies beyond what we can see? These questions, once the domain of philosophers and theologians, found new light under the lens of modern physics, and Hawking took it upon himself to bring these ideas to the world in a way that was both profound and accessible. Published in 1988, A Brief History of Time became an international sensation, selling millions of copies and captivating audiences far beyond the scientific community. Hawking, who was already a celebrated theoretical physicist, sought to explain complex ideas: black holes, relativity, quantum mechanics, the nature of time itself, to readers who had never studied physics. The book's appeal lay not only in its subject matter, but in its author, a man whose own battle with a debilitating illness, amyotrophic lateral sclerosis, ALS, made his intellectual triumphs all the more inspiring. Confined to a wheelchair, communicating through a voice synthesizer, Hawking defied all odds, unraveling the mysteries of the cosmos with nothing but the power of his mind. The book's impact was immediate and profound, but it was not without controversy. While Hawking aimed to make physics accessible, many readers found the concepts challenging, leading to debates about whether the book was truly reader-friendly. Others questioned his discussions on the nature of God, determinism, and the ultimate fate of the universe. Still, its influence remained undeniable, bridging the gap between science and the public in a way that few books had done before. Now, as we embark on this journey through a brief history of time, we will explore Hawking's revolutionary ideas in a way that captures both their complexity and their wonder. From the Big Bang to black holes, from Einstein's relativity to the uncertainty of quantum mechanics, we will follow the thread of discovery that has shaped our understanding of reality itself. This is not just a book about science. It is a book about human curiosity, the relentless pursuit of knowledge, and the deep desire to understand our place in the universe. And so, let us begin. For as long as humans have gazed at the night sky, they have asked questions about the nature of the universe. What are those twinkling lights above us? What lies beyond them? Has the universe always been here, or did it have a beginning? And if it began, what existed before it? These questions, which have fascinated philosophers and scientists alike for millennia, form the foundation of Stephen Hawking's A Brief History of Time. In the first part of this journey, we delve into the history of these cosmic inquiries, tracing the evolution of our understanding from ancient civilizations to modern physics. For much of human history, the universe was a mysterious, unknowable entity. Ancient cultures devised elaborate myths to explain the cosmos, often attributing its creation to the work of gods or divine beings. The Babylonians saw the sky as a vast dome stretched over the earth, while the Egyptians imagined the sun traveling across the heavens in a celestial boat. The Greeks, however, began to take a more systematic approach. The philosopher Aristotle, writing in the 4th century BCE, proposed that the Earth was the center of the universe, surrounded by crystalline spheres that carried the stars and planets in perfect circular motion. This geocentric model, refined by Ptolemy in the 2nd century CE, would dominate scientific thought for over 1,000 years. But even then, some thinkers dared to challenge conventional wisdom. In the 3rd century BCE, Aristarchus of Samos suggested that the sun, not the earth, was at the center of the cosmos. His ideas, however, were largely dismissed, buried under the weight of Aristotle and Ptolemy's influence. It wasn't until the Renaissance that the geocentric model faced its first serious challenge. In 1543, Nicolaus Copernicus published De Revolutionibus Orbium Celestium, proposing a heliocentric model where the Earth and other planets orbited the Sun. This idea, though revolutionary, was met with skepticism and resistance, especially from religious authorities. Then came Galileo Galilei, who, in the early 17th century, turned a telescope toward the heavens and saw things that no human had ever witnessed before. He observed moons orbiting Jupiter, proving that not all celestial bodies revolved around the Earth. He saw the phases of Venus, which could only be explained by a heliocentric system. Galileo's discoveries provided powerful evidence for Copernicus' model, but they also earned him the wrath of the Catholic Church, leading to his infamous trial and house arrest. With Galileo's findings, the foundation of our understanding had shifted, but it was Isaac Newton who provided the mathematical framework to describe the motion of celestial bodies. In Principia Mathematica, 1687, Newton formulated the laws of motion and universal gravitation, showing that the same force that pulls an apple to the ground also governs the movement of the planets. His equations described the universe as a grand, clockwork-like system, predictable, and governed by precise mathematical laws. For centuries, it seemed that Newton had provided the final answers, that the universe operated in a fixed, deterministic manner, where given enough information, one could predict the past and future of any object in motion. But as Hawking explains, this deterministic picture of the cosmos was eventually challenged. The 20th century brought new discoveries that would shake the very foundation of physics, leading to a deeper and more mysterious understanding of reality. One of the most significant breakthroughs came from Albert Einstein, whose theory of relativity reshaped our perception of space and time. Before Einstein, time was thought to be absolute, ticking away uniformly regardless of where one was in the universe. Space was simply a stage where events unfolded, unaffected by the objects within it. But Einstein showed that space and time were not separate entities. They were woven together into a single fabric known as space-time. He demonstrated that massive objects, like stars and planets, could bend this fabric, causing the force we experience as gravity. This insight, published in his General Theory of Relativity in 1915, led to astonishing predictions that light could be bent by gravity, that time could slow down in strong gravitational fields, and that the universe itself might not be static, but dynamic. At first, even Einstein resisted some of these implications. He He initially introduced a cosmological constant into his equations to maintain a static universe, believing that the cosmos must be unchanging. But in 1929, astronomer Edwin Hubble made a shocking discovery. Distant galaxies were moving away from us, and the farther they were, the faster they receded. This led to the realization that the universe was expanding. If the universe was expanding, then at some point in the past, it must have been much smaller, much denser, perhaps even originating from a single point. This idea laid the foundation for what would later be known as the Big Bang Theory, the notion that the universe began as an infinitely small, hot, and dense state before expanding into the cosmos we see today. This realization led to one of the most profound questions in physics. If the universe had a beginning, what caused it? Did time itself have a starting point? And if so, what existed before time began? These questions marked the beginning of a new era in cosmology, one that would blend relativity with an even stranger and more perplexing branch of physics, quantum mechanics. Quantum mechanics emerged in the early 20th century as scientists sought to understand the behavior of particles at the smallest scales. Unlike the predictable world of Newtonian physics, quantum mechanics revealed a universe of uncertainty, where particles could exist in multiple states at once, where events could be influenced by mere observation, and where chance played a fundamental role. This new framework clashed with classical physics, forcing scientists to rethink their understanding of reality. Hawking's work would sit at the crossroads of these two great revolutions, relativity and quantum mechanics. He sought to unite them, to develop a theory that could explain the universe at both the grandest scales, stars, galaxies, black holes, and the tiniest scales, subatomic particles. This quest would lead him to his groundbreaking work on black holes, where he discovered something astonishing. Black holes were not completely black. They could emit radiation, now known as Hawking radiation, slowly evaporating over time. This discovery challenged long-held assumptions and brought physics closer to a unified theory of everything. Thus, the story of the universe, as told in a brief history of time, is not just a story of stars and galaxies. It is a story of human curiosity, of the relentless pursuit of knowledge. It is a tale of ancient philosophers gazing at the sky, of Galileo defying the church, of Einstein bending time, and of Hawking unraveling the deepest secrets of the cosmos from his wheelchair. And this is just the beginning. The universe is vast, complex, and filled with mysteries that stretch beyond the limits of human comprehension. Yet for all its grandeur, it obeys rules, mathematical laws that govern its movements, its birth, and perhaps even its eventual fate. In the previous part, we explored the historical evolution of our understanding of the cosmos, from the geocentric views of ancient philosophers to the revolutionary ideas of Newton, Einstein, and beyond. Now, we dive deeper into one of the most fascinating and fundamental questions in physics. What is the nature of time? Time is something we experience every moment of our lives. It flows forward, never backward. We grow older, events unfold in sequence, and the past remains behind us while the future lies ahead. But why does time move in one direction? What exactly is time, and does it have a beginning or an end? These are questions that scientists and philosophers have wrestled with for centuries, and in a brief history of time, Hawking takes us on a journey to unravel the secrets of time itself. To understand time, we must first revisit Einstein's theory of relativity. Before Einstein, time was thought to be absolute, ticking away at the same rate for everyone, regardless of location or movement. Newton imagined a universe where time flowed independently of space, like a great cosmic clock. But Einstein's theory shattered this idea. He demonstrated that time and space were not separate entities, but rather part of a single continuum known as space-time. In this new understanding, time could stretch and contract, moving at different rates depending on an observer's speed and position in a gravitational field. One of the most astonishing predictions of relativity is time dilation. Imagine two identical clocks, one on Earth and the other aboard a spaceship traveling at nearly the speed of light. If we compared these clocks, we would find that time on the moving spaceship ticks more slowly than time on Earth. In other words, an astronaut traveling at near light speeds would age more slowly than people left behind on Earth. This effect, though counterintuitive, has been confirmed by experiments using highly accurate atomic clocks placed on fast-moving jets. Time, as Einstein showed, is not fixed. It is relative, influenced by speed and gravity. But gravity does more than just bend time. It can also stop it entirely. According to general relativity, the stronger the gravitational field, the slower time moves. Near a massive object, like a black hole, gravity is so intense that time itself can come to a standstill. If an astronaut were to approach the edge of a black hole, what physicists call the event horizon, they would appear frozen in time to an outside observer. To the astronaut, however, time would continue as normal, but they would never be able to return, forever trapped in the gravitational pull of the singularity. This idea raises profound questions. If time can slow down and even stop, does that mean it had a beginning? Could it one day come to an end? To answer this, we must look at the concept of the arrow of time. In our daily lives, time appears to have a clear direction. A cup of coffee cools down, never heats up on its own. A broken glass shatters, but never spontaneously reassembles. This one-way movement of time is governed by the second law of thermodynamics, which states that entropy, the measure of disorder, always increases in a closed system. Entropy is why we experience time as moving forward. The universe began in a highly ordered state, with energy concentrated in a small, hot, and dense singularity, the Big Bang. As the universe expanded, entropy increased, spreading matter and energy outward in a more disordered fashion. This increase in disorder is what gives time its direction. In a universe where entropy always increases, time must move forward. But this raises a paradox. If entropy dictates the arrow of time, what happens if the universe reaches a state of maximum entropy, where all matter and energy are evenly distributed? Does time stop? Will the universe cease to change? Some physicists speculate that the universe could reach a heat death, where no usable energy remains, and time effectively loses its meaning. Others propose that the universe could eventually collapse back into a singularity, leading to a new Big Bang, a cycle of death and rebirth, where time resets itself. Hawking, however, introduced another idea, that time might not have had a beginning in the conventional sense. He suggested that, when we trace time backward to the moment of the Big Bang, classical physics breaks down, and quantum mechanics takes over. In this quantum realm, time behaves differently, and rather than having a singular starting point, it may resemble a smooth, curved surface like the North Pole of the Earth. In this view, asking what happened before the Big Bang is like asking what is north of the North Pole. The question loses its meaning because time itself emerges from the fabric of space. This idea ties into the concept of imaginary time, a theoretical construct introduced by Hawking. Imaginary time is not the time we experience, but a mathematical tool that allows physicists to describe the universe in ways that avoid singularities. If time is treated as a dimension similar to space, then rather than having a definite starting point, the universe could exist in a state where time has no true beginning or end, just as a sphere has no true edge. But does this mean time is an illusion? If time is flexible, affected by gravity and motion, and possibly without a true beginning, does it even exist in the way we perceive it? Some physicists argue that time may be an emergent property rather than a fundamental aspect of the universe. It could arise from the interactions of particles at the quantum level, much like temperature emerges from the movement of molecules. Others speculate that time may not be continuous, but rather made up of tiny, discrete units, like frames in a film. Regardless of these theoretical debates, time remains one of the greatest mysteries in physics. We experience it every day, yet we barely understand its nature. Hawking's insights push us to rethink what we know, challenging our assumptions about reality itself. If time is not absolute, if it can stretch, bend, stop, or even cease to exist, then what does that mean for our understanding of the universe and for our place within it? As we move forward in our journey through a brief history of time, we will explore even deeper mysteries, the strange world of quantum mechanics, the enigma of black holes, and the ongoing search for a theory that unites all of physics. For now, we leave with a deeper appreciation of time's complexity, a force so familiar, yet so profoundly mysterious. As we continue our journey through a brief history of time, we now step into the realm of the smallest scales imaginable, the strange and unpredictable world of quantum mechanics. While Einstein's theory of relativity describes the grand architecture of the universe, quantum mechanics reveals a universe that is far less intuitive, where certainty gives way to probability, and where particles do not behave as we expect. Understanding quantum mechanics is crucial to modern physics because, as Hawking explains, the universe is not only vast, but also fundamentally built from the tiniest building blocks of reality, particles that follow rules unlike anything we encounter in everyday life. To appreciate the significance of quantum mechanics, we must first understand why classical physics, which worked so well for centuries, was unable to explain certain fundamental phenomena. Before the 20th century, physicists largely believed in a deterministic universe, one where, if you knew all the forces at play, you could predict everything that would ever happen. Newton's laws could explain the motion of planets, falling objects, and even the tides. However, as scientists began studying light and atomic behavior, they encountered phenomena that defied Newtonian physics. One of the earliest mysteries that led to quantum mechanics was the problem of blackbody radiation. When objects are heated, they emit light, first appearing red, then orange, and eventually white hot as the temperature increases. Classical physics predicted that, at high temperatures, an object should emit an infinite amount of ultraviolet and even X-ray radiation, a paradox known as the ultraviolet catastrophe. But this did not match reality. Objects emitted a finite amount of energy. In 1900, Max Planck proposed a radical idea. Instead of energy being emitted continuously, it was released in discrete packets, or quanta. This was the birth of quantum theory, though even Planck himself did not fully grasp the significance of his discovery at the time. A few years later, Albert Einstein built upon this idea while studying the photoelectric effect. He proposed that light itself was made of tiny particles, or photons, that carried energy in discrete packets. This explanation not only solved the mystery of how light interacted with matter, but also won Einstein the Nobel Prize in Physics. His work laid the foundation for quantum mechanics, even as he later struggled to accept its more unsettling implications. The real revolution in quantum mechanics came in the 1920s with Werner Heisenberg and Erwin Schrödinger. Heisenberg's uncertainty principle shattered the idea that we could ever predict the exact location and momentum of a particle simultaneously. In other words, the more precisely we know where a particle is, the less we know about how fast it is moving, and vice versa. This was a fundamental departure from classical physics, which assumed that, given enough information, the future could be determined precisely. Quantum mechanics, however, revealed a universe where chance played an intrinsic role. Schrödinger, on the other hand, introduced the wave function, an equation that described the probability of where a particle might be, rather than pinpointing its exact location. His famous thought experiment, Schrödinger's cat, illustrated the bizarre implications of quantum mechanics. He imagined a cat placed in a sealed box with a radioactive atom that had a 50% chance of decaying and releasing poison. Until someone opened the box to observe, the cat was neither dead nor alive, but existed in a strange superposition of both states. This paradox highlighted the problem of measurement in quantum mechanics. Particles could exist in multiple states at once until observed, at which point they collapsed into a definite state. This concept, known as wave function collapse, remains one of the great mysteries of quantum mechanics. Why does observing a quantum system force it to take on a single outcome? Some physicists suggest that measurement itself affects reality, while others propose that all possible outcomes actually happen, splitting the universe into multiple realities, an idea known as the many worlds interpretation. If this is true, then every time a decision is made, the universe branches into parallel realities, each following a different outcome. Quantum mechanics also introduced another strange phenomenon, quantum entanglement. When two particles become entangled, their states remain linked no matter how far apart they are. If you measure one particle, the other instantly assumes a corresponding state, even if they are light years apart. This phenomenon, which Einstein called spooky action at a distance, has been experimentally verified. Yet it remains one of the most puzzling aspects of reality. It suggests that information can travel instantaneously across vast distances, seemingly violating the speed limit of light set by relativity. For Stephen Hawking, quantum mechanics was not just a set of abstract principles. It was essential to understanding the nature of the universe itself, particularly black holes. Classical physics predicted that nothing, not even light, could escape from a black hole's gravitational pull. But Hawking's groundbreaking work in the 1970s showed that when quantum effects are considered, black holes are not entirely black. They emit a faint radiation, now known as Hawking radiation. This discovery was revolutionary because it suggested that black holes could slowly evaporate over time, losing mass and eventually disappearing. This created a paradox. If information fell into a black hole and the black hole eventually vanished, where did that information go? According to quantum mechanics, information about a system's past states cannot be destroyed. Yet black holes seem to erase information from the universe. This became known as the black hole information paradox, one of the greatest unresolved questions in physics. Hawking's work on black holes demonstrated the need for a unified theory, one that could reconcile quantum mechanics with general relativity. While relativity governs the behavior of large objects like stars and galaxies, quantum mechanics rules the tiny realm of particles. Yet, when these two theories meet, such as inside a black hole or at the moment of the Big Bang, they seem to break down, producing mathematical infinities that make no physical sense. The quest for a theory of everything, a single framework that explains all forces in nature, remains one of the greatest challenges in modern physics. Several candidates have emerged, including string theory, which proposes that fundamental particles are not points, but tiny vibrating strings, and loop quantum gravity, which attempts to quantize space-time itself. Hawking believed that a unified theory might one day be discovered, but he also acknowledged that it might never be fully understood by humans. As we move forward in a brief history of time, we will explore deeper into the mysteries of black holes, the nature of the universe's expansion, and the ultimate fate of everything that exists. The laws of physics may seem unbreakable, but as quantum mechanics has shown, reality is far stranger than we ever imagined. The universe is full of mysteries, some hidden in the smallest quantum scales, others lurking in the vast cosmic expanse. Few things are as mysterious and awe-inspiring as black holes, regions of space where gravity is so intense that nothing, not even light, can escape. These cosmic phenomena are more than just celestial oddities. They challenge the very foundations of physics, forcing us to question our understanding of space, time, and reality itself. In previous parts, we explored how Einstein's general relativity reshaped our understanding of gravity, showing that massive objects bend space-time, influencing the movement of everything around them. But when relativity meets quantum mechanics at the heart of a black hole, the laws of physics begin to break down. In this part, we will dive into the strange and mind-bending world of black holes, their properties, and their impact on our understanding of the universe. The concept of a black hole dates back much further than Einstein. In the 18th century, English scientist John Michell first speculated about the existence of what he called dark stars, celestial bodies so massive that their gravity would prevent even light from escaping. However, without the understanding of relativity, this idea remained speculative for centuries. It wasn't until Karl Schwarzschild, a German physicist, solved Einstein's equations for a spherical mass in 1916 that the true nature of black holes became clear. His solution described a point in space where gravity became infinite, what we now call a singularity, surrounded by an invisible boundary known as the event horizon. The event horizon is one of the defining features of a black hole. It marks the point of no return. Anything that crosses it is forever trapped, unable to escape the immense gravitational pull. If you were to approach a black hole, you would experience a strange phenomenon known as gravitational time dilation. Time would slow down relative to an outside observer, stretching seconds into minutes, minutes into hours. If you were to fall past the event horizon to the outside world, you would appear frozen in time, slowly fading away as the black hole's gravitational pull stretched light into longer wavelengths. But to you, time would continue normally, and before you even realized it, you would be pulled inexorably toward the singularity at the black hole's core. What happens inside a black hole remains one of the greatest mysteries in physics. General relativity predicts that matter collapses into an infinitely dense point, a singularity where space-time itself ceases to exist. At this point, our current understanding of physics breaks down. Our equations produce infinities that defy comprehension. Some physicists believe that a deeper theory, one that unites quantum mechanics and gravity, is needed to fully explain what occurs within a black hole. Hawking made one of the most groundbreaking discoveries about black holes when he applied quantum mechanics to their behavior. For decades, black holes were thought to be absolute. Once something fell in, it was gone forever. However, in 1974, Hawking proposed that black holes were not entirely black. They emitted a faint radiation, now known as Hawking radiation. This revelation was profound because it suggested that black holes could eventually evaporate, losing mass over time. Hawking radiation arises from the strange effects of quantum mechanics near the event horizon. In the vacuum of space, particles and antiparticles constantly appear and annihilate each other in pairs. But near a black hole, one of these particles can fall in while the other escapes, leading to a gradual loss of energy. Over immense timescales, a black hole could shrink and eventually disappear. This discovery challenged the long-held belief that black holes were eternal, introducing a paradox that remains unresolved to this day. This paradox is known as the black hole information paradox. According to the principles of quantum mechanics, information about a physical system can never be truly destroyed. Yet, if a black hole eventually evaporates, what happens to the information that fell into it? Is it lost forever, violating the fundamental laws of physics? Or is it somehow preserved, perhaps encoded in the radiation itself? Various theories attempt to resolve this paradox. Some suggest that information is stored on the event horizon in a holographic form, an idea inspired by the holographic principle proposed by physicists Gerard T. Hooft and Leonard Susskind. Others believe that the information might leak out over time in Hawking radiation, but this would require modifications to our understanding of quantum mechanics. A more radical idea is that when a black hole evaporates, it leaves behind a remnant, a small, stable object that retains the lost information. However, no direct evidence for such remnants exists. The study of black holes is not just a theoretical exercise. It has real, observable consequences in our universe. In 2019, the Event Horizon Telescope collaboration captured the first ever image of a black hole, located in the center of the galaxy M87. This groundbreaking achievement provided visual confirmation of Einstein's predictions, showing the shadow of the event horizon surrounded by a glowing ring of superheated gas. More recently, astronomers have studied gravitational waves, ripples in space-time caused by black hole mergers, providing further evidence of their existence and behavior. Hawking's work on black holes was not only about solving theoretical puzzles, it was about pushing the boundaries of human knowledge, showing that even the most extreme and mysterious objects in the universe obey physical laws. He believed that understanding black holes could lead to a deeper understanding of the cosmos itself. One of the most fascinating implications of black hole physics is its connection to the early universe. If tiny primordial black holes formed in the moments after the Big Bang, they could provide clues about the conditions of the early cosmos. Some scientists even speculate that dark matter, the invisible substance that makes up most of the universe's mass, could consist of small black holes. Black holes also force us to reconsider the nature of time and space. Some theories propose that black holes could act as portals to other regions of the universe, or even to different universes entirely. While the idea of wormholes, shortcuts through space-time, remains speculative, it is based on real equations from general relativity. If such phenomena exist, they could revolutionize our understanding of space travel and the structure of reality. Hawking's contributions to black hole physics remain among his most enduring legacies. He demonstrated that even in the face of cosmic mystery, the human mind is capable of uncovering profound truths. His work not only advanced our understanding of the universe, but also inspired countless scientists to continue exploring the unknown. As we move forward in a brief history of time, we will explore even greater questions. How did the universe begin? What is its ultimate fate? And is there a final, unifying theory that explains everything? Black holes, in many ways, serve as a gateway to these larger mysteries, reminding us that the cosmos is far stranger and more fascinating than we could ever imagine. And so, the journey continues. As we continue our exploration of a brief history of time, we arrive at one of the most profound questions in cosmology. How did the universe begin? And what laws governed its earliest moments? The answers lie in the study of the Big Bang, the cosmic event that marked the birth of everything we know. Yet, the further we look back in time, the more our conventional understanding of physics begins to break down. The idea that the universe had a definite beginning was not always accepted. For centuries, many scientists and philosophers believed that the universe was eternal and unchanging, following the ancient Aristotelian view. Even Einstein, when developing his equations of general relativity, initially resisted the idea of a dynamic universe, introducing a cosmological constant to keep the universe static. However, in the early 20th century, observations began to challenge this view. In 1929, Edwin Hubble made a groundbreaking discovery that would reshape our understanding of the cosmos. He observed that distant galaxies were moving away from us, and the farther they were, the faster they appeared to be receding. This was evidence that the universe was expanding, a realization that led to the inescapable conclusion: if the universe is expanding now, then in the past, it must have been smaller. If we rewind time far enough, all matter and energy in the universe must have been compressed into an incredibly dense and hot state, a singularity. This moment of creation is what we call the Big Bang. The term Big Bang was originally coined by physicist Fred Hoyle, who was actually opposed to the idea. He championed the steady-state model, which proposed that the universe had always existed and was continuously forming new matter to maintain its density. However, observational evidence continued to mount in favor of the Big Bang theory. One of the strongest pieces of evidence came in 1964, when Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background radiation, CMB. This faint glow of radiation, detected in every direction of the sky, was the afterglow of the Big Bang itself, a remnant of the early universe when it was hot and dense. The discovery of the CMB provided direct confirmation that the universe had once been in a much hotter and more compact state. But what exactly happened in the first moments after the Big Bang? The laws of physics, as we know them, can describe the universe back to a fraction of a second after its birth. But beyond that, we enter the realm of speculation and theoretical physics. In the first 10 seconds, the universe underwent an extraordinary period of rapid expansion known as inflation, proposed by physicist Alan Guth in the 1980s. The theory of inflation suggests that the universe expanded exponentially faster than the speed of light for a tiny fraction of a second. This explains why the universe appears so uniform today, why distant regions of space have nearly the same temperature and density, despite being too far apart to have ever interacted under normal circumstances. Without inflation, these regions would have had no time to communicate before they became so widely separated. After inflation ended, the universe was a hot, dense soup of particles and radiation. During the first few minutes, nuclear reactions took place, forming the first atomic nuclei in a process called Big Bang nucleosynthesis. Hydrogen and helium, the two lightest elements, were produced in vast quantities, laying the foundation for all future stars and galaxies. As the universe continued to expand and cool, it reached a critical point about 380,000 years after the Big Bang. This is when atoms first formed, allowing light to travel freely through space for the first time. Before this moment, the universe was an opaque plasma, where photons, particles of light, constantly scattered off free electrons. Once atoms formed and electrons were bound to nuclei, the universe became transparent. The light from this era is what we now detect as the cosmic microwave background radiation. From this early structureless universe, gravity began its work. Tiny variations in the density of matter caused some regions to have slightly stronger gravitational pulls than others, slowly drawing in more material. Over millions of years, these fluctuations grew, leading to the formation of the first stars and galaxies. The formation of stars was a crucial milestone. In their fiery cores, nuclear fusion produced heavier elements, from carbon and oxygen to iron and beyond. When these stars died in massive explosions called supernova, they scattered these elements into space, seeding the formation of planets and eventually life itself. Every atom in your body, every carbon atom in your DNA, every oxygen molecule you breathe was forged in the heart of a star billions of years ago. While the Big Bang explains the origin of the universe, it also raises profound questions. What caused the Big Bang? Did time itself begin at that moment, or was there something before it? The theory of general relativity predicts that the universe began as a singularity, an infinitely dense point where the laws of physics break down. However, singularities are a sign that our theories are incomplete. To truly understand the beginning of the universe, we need a theory that unifies quantum mechanics with gravity. Stephen Hawking, along with physicist James Hartle, proposed one of the most intriguing ideas about the origin of the universe, the no-boundary proposal. According to this model, space and time are not separate entities, but are linked in such a way that the universe had no singular beginning. Instead of emerging from a singularity, the early universe can be thought of as a smooth, finite region, like the surface of a sphere. Just as the Earth's surface has no edge, the universe could have had no definite beginning. Time itself could have emerged smoothly from a quantum state. This idea challenges our intuitive notions of time. We tend to think of time as a straight line, with a clear starting point. But if the no-boundary proposal is correct, the universe may have never had a sharp beginning. It simply existed in a different form before transitioning into the expanding universe we observe today. Despite these advances, many mysteries remain. Is our universe the only one? Or is it part of a larger multiverse where countless other universes exist with different laws of physics? Could our universe have undergone cycles of expansion and contraction, with multiple Big Bangs occurring over time? The search for answers continues, with new observations from powerful telescopes, experiments in particle physics, and developments in quantum gravity theories like string theory and loop quantum gravity. What is clear is that the universe is not static or unchanging. It is dynamic, evolving, and full of surprises. Hawking's exploration of the origins of the universe was not just a scientific pursuit. It was a quest to understand our place in the cosmos. By uncovering the history of the universe, we gain insight into where we came from and perhaps even where we are headed. As we continue our journey through a brief history of time, we will explore what lies ahead for the universe. Will it expand forever, or will it one day collapse back in on itself? What ultimate fate awaits the cosmos? The answers to these questions are not just matters of science. They touch on the deepest philosophical and existential questions of all. As we venture further into a brief history of time, we move from the origins of the universe to its future. What will happen to the cosmos in the distant ages to come? Will it continue to expand forever, growing colder and darker until all life ceases? Or will it someday reverse course, collapsing back into itself in a final cataclysmic event? These are some of the biggest questions in cosmology, and they remain the subject of intense scientific debate. To understand the fate of the universe, we must first explore the forces that govern its expansion. As we discussed in previous parts, the discovery that the universe is expanding was one of the most revolutionary findings in modern physics. But what determines how this expansion unfolds over time? The answer lies in a delicate balance between the outward push of expansion and the inward pull of gravity. Imagine throwing a ball into the air. If gravity is strong enough, it will eventually pull the ball back down. But if you throw it hard enough, past a certain velocity, it will escape Earth's gravity and continue moving outward forever. The same principle applies to the universe. If the force of expansion is weaker than gravity, the universe will eventually slow down and collapse. If if expansion is strong enough, the universe will keep growing forever. Scientists have proposed several possible scenarios for how the universe's future might unfold. These scenarios depend largely on one crucial factor: the density of matter and energy in the cosmos. One possibility is the Big Crunch. In this scenario, if the density of the universe is high enough, gravity will eventually overcome expansion. The universe will slow down, then reverse direction, collapsing inward. Galaxies will be drawn closer together, stars will merge, and temperatures will rise as everything is crushed into a final singularity, a mirror image of the Big Bang. Some theories even suggest that this singularity could trigger another Big Bang, leading to a cyclic universe where expansion and contraction occur in endless repetition. Another possibility is the Big Chill, or heat death. If the density of matter is too low, expansion will continue indefinitely. Over billions of years, galaxies will drift apart, stars will burn out, and the universe will grow colder and darker. With no new sources of energy, all motion will eventually stop, and the cosmos will become a vast, empty expanse of black holes and decaying radiation. This scenario paints a bleak but scientifically plausible picture: a universe that simply fades into darkness, never collapsing, but never producing anything new. A third, more extreme scenario is the Big Rip. This outcome depends on a mysterious force known as dark energy, which appears to be accelerating the expansion of the universe. If dark energy grows stronger over time, it could eventually tear apart everything, not just galaxies, but stars, planets, and even atoms themselves. In this case, the fabric of space-time would be pulled apart completely, leaving behind nothing but a void. The discovery of dark energy in the late 1990s changed the way scientists think about the universe's future. Before then, most believed that the expansion of the universe was slowing down due to gravity. But observations of distant supernova showed that the expansion is actually accelerating. This was an unexpected and deeply puzzling finding. What could be causing this acceleration? Dark energy remains one of the greatest mysteries in physics. Unlike ordinary matter, which clumps together due to gravity, dark energy acts as a repulsive force, pushing the universe outward. Some scientists believe it is related to the energy of empty space itself, as described by Einstein's cosmological constant. Others suggest it could be evidence of an unknown force or a fundamental flaw in our understanding of gravity. Whatever its true nature, dark energy dominates the universe. Observations indicate that ordinary matter, the stuff that makes up stars, planets, and people, accounts for less than 5% of the universe's total content. Dark matter, a mysterious, invisible substance that influences galaxy formation, makes up about 27%. The rest, nearly 70%, is dark energy, driving the acceleration of cosmic expansion. The implications of dark energy are profound. If it continues to act as it does now, the Big Chill scenario seems the most likely fate for the universe. But if its properties change over time, other outcomes, like the Big Rip or a future collapse, could be possible. Stephen Hawking was deeply interested in these questions, particularly in how quantum mechanics and gravity might shape the long-term fate of the cosmos. His work suggested that black holes, which play a key role in cosmic evolution, could slowly evaporate over time due to Hawking radiation. If true, this would mean that in a universe destined for heat death, even black holes would eventually disappear, leaving behind only faint traces of energy. But could there be another way? Some physicists speculate that quantum mechanics might allow for unexpected twists in the universe's fate. If the laws of physics permit the formation of new universes, perhaps through quantum fluctuations or the collapse of black holes into baby universes, then the end of one cosmos might simply be the beginning of another. This idea, while speculative, aligns with Hawking's vision of a universe governed by deep and mysterious rules that we have only begun to understand. Beyond the fate of the universe itself, these questions have profound philosophical implications. If the cosmos will one day end, does that make human existence meaningless? Or does it instead highlight the incredible beauty of our fleeting moment in time? Hawking often emphasized that understanding the universe's fate is not just about abstract physics. It is about our place within the grand story of existence. At its core, A Brief History of Time is not just a book about science, but about the human quest for knowledge. From ancient philosophers to modern physicists, humanity has sought to understand the cosmos, to make sense of its vastness and its mysteries. The fact that we can even ask these questions is in itself remarkable. As we move forward, we will explore some of the biggest unanswered questions in physics. What is time? Can we travel through it? And is there a final, ultimate theory that can explain everything? These questions bring us to the very edge of what we know, and into the realm of what remains to be discovered. As we journey further through A Brief History of Time, we arrive at one of the most profound and puzzling questions in modern physics, the nature of time itself. We take time for granted in our daily lives. It flows in one direction, from past to future, seemingly constant and unwavering. But is time really as simple as it appears? Or is it a deeper and more complex aspect of the universe, governed by hidden laws that we have yet to fully understand? At the heart of this discussion is a fundamental mystery. Why does time have a direction? Unlike space, which allows movement in any direction, forward, backward, left, right, up, or down, time seems to flow in only one way. This is what physicists call the arrow of time. But what determines this direction? If the laws of physics work the same whether time moves forward or backward, why do we only experience it moving in one way? One of the key insights into the arrow of time comes from the second law of thermodynamics. This law states that in any closed system, entropy, the measure of disorder, always increases over time. Imagine a cup of hot coffee placed in a room. Over time, the heat spreads out and the coffee cools down. But the reverse never happens. You never see a cold cup of coffee suddenly absorbing heat from the air and becoming hot again. This tendency for things to move from order to disorder is what gives time its apparent direction. Entropy provides a powerful explanation for why we experience time moving forward. In the early universe, right after the Big Bang, everything was in a highly ordered, low entropy state. As the universe expanded, it became more disordered, with galaxies forming, stars burning fuel, and complex structures emerging. The increase in entropy creates a distinction between past and future, defining what we call the arrow of time. But if entropy determines the flow of time, does that mean time itself is just an illusion? Could the universe exist in a way where time runs backward? This idea has been explored in theoretical physics, but it raises deep paradoxes. If time were reversed, our memories would also work in reverse, making it impossible to perceive the change. In other words, if we lived in a world where entropy was decreasing, we wouldn't notice. It would just seem like time was still moving forward from our perspective. This leads to an even bigger question. Is time a fundamental part of the universe? Or is it something that emerges from deeper physical laws? Some physicists argue that time might not be a basic feature of reality at all, but rather a property that arises from interactions between particles and forces. If this is true, then the flow of time as we experience it might be just a convenient illusion, one that emerges from the way our brains process information. Einstein's theory of relativity gives us another reason to question our everyday understanding of time. One of the most startling predictions of relativity is that time is not absolute. Instead, it is relative, meaning that it depends on the speed of an observer and the strength of the gravitational field they are in. This concept, known as time dilation, has been confirmed by countless experiments. For example, astronauts aboard the International Space Station experience time slightly differently than people on Earth. Because they are moving at high speeds relative to the planet, time moves slightly slower for them. Over the course of their mission, this effect is small, just a fraction of a second. But if they were traveling at speeds close to the speed of light, the effect would be much more dramatic. Gravity also affects time. The stronger the gravitational field, the slower time moves. This phenomenon was first predicted by Einstein's general theory of relativity and has been confirmed in experiments with highly accurate atomic clocks. A clock placed at the top of a mountain will run slightly faster than a clock at sea level because the strength of Earth's gravity decreases with altitude. This effect, though tiny in everyday life, becomes significant near extremely massive objects like black holes. This brings us to one of the most intriguing ideas in modern physics: time travel. If time is flexible, able to stretch and shrink depending on speed and gravity, could it be possible to travel through time? The equations of relativity suggest that under certain extreme conditions, time travel could be theoretically possible. One proposed method is traveling close to the speed of light. If a spaceship could accelerate to near light speeds, time on board would slow down relative to the rest of the universe. For the crew, only a few years might pass, while centuries or even millennia pass for those left behind. This kind of one-way time travel is not just theoretical. It is supported by experimental data and the known laws of physics. A more exotic possibility is using wormholes, hypothetical shortcuts through space-time that could connect distant points in space and time. If a wormhole could be stabilized, which would require a form of negative energy that we have not yet discovered, it might allow for travel between different eras of history. However, wormholes remain purely theoretical, with no experimental evidence to suggest they actually exist. There is also the famous concept of a closed time-like curve, a solution in Einstein's equations that theoretically allows an object to travel in a loop through time. If such a loop could exist, it might permit travel to the past. But here, we run into one of the most famous problems of time travel, the grandfather paradox. If you traveled back in time, and prevented your grandfather from meeting your grandmother, you would never be born. But if you were never born, then you could never have traveled back in time in the first place. Some physicists argue that paradoxes like this suggest time travel to the past is impossible. Others believe that the universe might resolve such paradoxes through self-consistency, meaning that events would always unfold in a way that prevents contradictions. For example, if you traveled back in time, you might find that every action you take somehow preserves the past rather than changing it. One of the most fascinating ideas related to time travel is the many worlds interpretation of quantum mechanics. This theory suggests that every possible outcome of an event actually happens, but in separate, parallel universes. If this is true, then traveling to the past might not change the original timeline at all. It might simply create a new branch of reality. This idea, while speculative, has gained interest in both science and science fiction. Stephen Hawking was skeptical about the possibility of time travel to the past. He even proposed the chronology protection conjecture, which suggests that the laws of physics prevent time travel paradoxes from occurring. If true, this would mean that nature itself imposes a kind of cosmic censorship, stopping any situation where someone could interfere with their own past. Yet, even if backward time travel remains impossible, the study of time is far from over. Understanding the true nature of time, whether it is fundamental or emergent, whether it has a beginning or an end, remains one of the greatest challenges in physics. As we move forward in a brief history of time, we will explore another deep mystery: the search for a single, unified theory that can explain all the forces of nature. The quest for a theory of everything is one of the most ambitious goals in science. And in the next part, we will dive into the competing ideas that seek to unravel the deepest secrets of the universe. As we journey deeper into a brief history of time, we arrive at one of the most ambitious goals in all of physics: the search for a theory of everything, a single, unified framework that explains all the fundamental forces governing the universe. Scientists have long sought such a theory, believing that if we could discover it, we would unlock the deepest secrets of reality itself. But how close are we to this ultimate understanding? And what challenges stand in our way? To understand why a theory of everything is so elusive, we must first look at the four fundamental forces that govern nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These forces shape everything from the motion of galaxies to the structure of atoms, yet they operate in very different ways. Gravity, as described by Einstein's general relativity, is the weakest of the four forces, but has an infinite range. It governs the movement of planets, stars, and the expansion of the universe. Electromagnetism, the force responsible for electricity, magnetism, and light, is much stronger than gravity and plays a crucial role in chemistry and biology. Then there are the nuclear forces, the strong nuclear force, which holds atomic nuclei together, and the weak nuclear force, which governs radioactive decay and is essential for processes like nuclear fusion in the sun. In the 20th century, physicists made remarkable progress in unifying some of these forces. They discovered that electromagnetism and the weak nuclear force could be combined into a single framework known as the electroweak force. This unification was a major breakthrough and was later confirmed by experiments. The strong nuclear force was also successfully explained using quantum chromodynamics, QCD, a theory that describes how fundamental particles called quarks interact via particles called gluons. These advances led to what is now called the Standard Model of particle physics, a highly successful theory that describes 3 of the 4 fundamental forces with astonishing precision. However, there is one major problem. Gravity is not included in this framework. Unlike the other forces, gravity is best described not by quantum mechanics, but by Einstein's general theory of relativity. This theory tells us that gravity is not a force in the traditional sense, but rather a curvature of space-time caused by mass and energy. While general relativity works perfectly on large cosmic scales, it clashes with quantum mechanics, which governs the behavior of particles at the smallest scales. Here lies one of the biggest challenges in physics. How do we reconcile gravity with quantum mechanics? The 2 theories are fundamentally different in their descriptions of reality. Quantum mechanics deals with probabilities and uncertainty, while general relativity describes a smooth, continuous fabric of space-time. Whenever physicists attempt to combine them, the equations break down, producing infinite and nonsensical results. One possible solution is quantum gravity, a theoretical framework that would describe gravity in quantum terms. Several approaches have been proposed, but none have been experimentally confirmed. Among the leading candidates is string theory, which suggests that all particles and forces arise from tiny vibrating strings. In this view, the universe is not made of point-like particles, but of fundamental strings that exist in multiple dimensions beyond the familiar 3 of space and 1 of time. String theory is fascinating because it naturally includes gravity, offering a possible path toward unification. It also predicts the existence of extra dimensions beyond the ones we perceive, which could help explain some of the mysteries of particle physics. However, there is a major problem. String theory has yet to make any testable predictions. Because the energy scales involved are far beyond what current experiments can reach, it remains a largely mathematical framework without direct experimental support. Another competing idea is loop quantum gravity, which attempts to quantize space-time itself. Instead of treating space and time as a continuous fabric, this theory suggests that space-time is made up of discrete units, or quanta. This approach avoids some of the mathematical problems of string theory, but it has its own challenges and remains incomplete. Hawking himself made significant contributions to this search for a unified theory. One of his most important insights came from studying black holes, specifically how they interact with quantum mechanics. His discovery of Hawking radiation showed that black holes are not completely black. They emit tiny amounts of radiation due to quantum effects near their event horizons. This was one of the first hints that gravity and quantum mechanics might be connected in unexpected ways. Hawking believed that a theory of everything might not only explain the forces of nature, but also shed light on the origin of the universe itself. If we could fully understand the laws governing space, time, and matter, we might finally uncover what happened at the very beginning of the cosmos, before even the Big Bang. Yet, Hawking also cautioned that such a theory might never be completely within our reach. In his later years, he speculated that the universe might be fundamentally unpredictable at the deepest levels, governed by probabilities rather than strict laws. If true, this would mean that rather than finding a single, elegant equation that explains everything, we may have to accept a more complex and probabilistic understanding of reality. Despite these challenges, the search for a unified theory remains one of the most exciting frontiers in physics. New discoveries, such as insights from particle accelerators, observations of black holes, and advances in quantum computing, may eventually provide the missing pieces needed to complete the puzzle. But beyond the scientific quest, the search for a theory of everything is also deeply philosophical. If we do find such a theory, what would it mean for us? Would it answer the deepest questions about existence, or would it simply raise new ones? As Hawking himself wrote, even if there is only one possible unified theory, it is just a set of rules and equations. What is it that breathes fire into the equations and makes a universe for them to describe? In the next part, we will explore one of the most intriguing ideas Hawking put forward: the possibility that the universe may not require a creator at all. What if the laws of physics allow the universe to emerge from nothing? How does quantum mechanics play a role in this grand mystery? As we near the final stages of a brief history of time, we arrive at one of the most profound and controversial questions in all of science. Does the universe require a creator? This question has been at the heart of philosophical and religious thought for centuries. But Stephen Hawking approached it from a scientific perspective, arguing that the laws of physics might allow the universe to emerge from nothing without the need for a divine creator. At first, this idea may seem counterintuitive. How can something come from nothing? Doesn't every effect require a cause? Throughout history, many have believed that the universe must have been created by a higher power, an uncaused first mover that set everything in motion. But as we've seen throughout our exploration of modern physics, the universe operates on principles that often defy our everyday intuition. One of the most groundbreaking developments in this debate comes from quantum mechanics, the branch of physics that governs the behavior of subatomic particles. Unlike classical physics, where objects follow predictable paths, quantum mechanics introduces an element of uncertainty and probability. Particles can pop in and out of existence, seemingly from nowhere, in what is known as quantum fluctuations. This concept is key to understanding Hawking's argument. If tiny particles can spontaneously appear and disappear at the quantum level, could an entire universe have emerged in a similar way? In the quantum realm, the idea of nothingness is not truly empty. It is a seething, energetic vacuum where fluctuations constantly occur. This challenges the traditional notion that nothing must mean complete absence. Instead, in quantum terms, nothing can still contain energy and potential. Hawking, along with physicist James Hartle, developed a theory known as the no-boundary proposal, which suggests that the universe has no singular starting point, no sharp beginning that requires an external cause. Instead of imagining the universe as having a defined moment of creation, this model envisions it as a self-contained entity, with time itself behaving in a way that removes the need for a creator. To understand this, imagine the surface of the Earth. If you travel south, you eventually reach the South Pole, but you don't ask, what's south of the South Pole? The question itself doesn't make sense because the South Pole is simply a point where certain directions cease to exist. Similarly, in the no-boundary model, asking what came before the Big Bang is meaningless because time itself did not exist in the way we perceive it today. The universe didn't begin from a singular point in time. It simply emerged, governed by the laws of quantum mechanics. Hawking's idea was radical because it removed the necessity of an external force to light the fuse of the Big Bang. If the universe could emerge spontaneously from quantum fluctuations, then the question of a creator, at least from a scientific standpoint, becomes unnecessary. In his own words, because there is a law such as gravity, the universe can and will create itself from nothing. Of course, this idea remains deeply controversial. While many physicists find the no-boundary proposal compelling, others argue that it does not fully explain why the laws of physics themselves exist in the first place. Even if the universe emerged from quantum fluctuations, what determined the rules that govern those fluctuations? Why does the universe have the properties it does? These are questions that remain open and continue to fuel philosophical debate. This discussion also ties into another major topic in modern cosmology, the multiverse hypothesis. If our universe could emerge spontaneously from quantum fluctuations, could other universes do the same? Some physicists believe that our universe may be just one of countless universes, each with different physical laws and conditions. This idea is supported by some interpretations of string theory and inflationary cosmology, which suggest that new universes could be continuously forming in an endless cosmic landscape. If the multiverse exists, it could explain one of the greatest mysteries in physics, why our universe appears so perfectly fine-tuned for life. The fundamental constants of nature, such as the strength of gravity, the charge of the electron, and the properties of atomic forces, seem to be precisely balanced to allow the existence of stars, planets, and ultimately life. If these constants were even slightly different, the universe as we know it might be uninhabitable. Some have taken this as evidence of a cosmic designer, an intelligent force that set the universe's parameters precisely to allow life to emerge. However, the multiverse hypothesis provides an alternative explanation. If there are an infinite number of universes, each with different physical laws, then it is not surprising that at least one of them, ours, happens to have the right conditions for life. We simply exist in a universe where life is possible because, in all the universes where it isn't, no one is there to ask the question. This idea is known as the anthropic principle. Hawking was intrigued by the multiverse idea, but remained cautious about its implications. Unlike theories that can be tested directly through experiments, the existence of other universes is difficult, if not impossible, to prove. While the mathematics suggests that the multiverse is a possibility, we currently have no observational evidence to confirm it. As such, it remains a fascinating but speculative idea. Even without invoking the multiverse, Hawking's argument is clear. The laws of physics alone may be sufficient to explain the emergence of the universe. If that is the case, then the traditional question of why is there something rather than nothing shifts from being a theological or philosophical mystery to a problem that can be studied scientifically. Of course, many people find these ideas unsettling. The notion that the universe does not require a divine creator challenges deeply held beliefs and raises new existential questions. If the universe is purely the result of natural laws, does it have any purpose? Is meaning something that must come from outside the universe, or is it something we create for ourselves? Hawking himself was often asked about his views on God and the meaning of life. He did not dismiss the possibility of a higher power entirely, but he emphasized that science does not need to invoke supernatural explanations to describe the universe. The scientific account is complete, he wrote, and theology is unnecessary. Yet, in his later years, he also acknowledged that the mystery of existence goes beyond mere equations. Even if we discover a complete theory of everything, there will still be the question of why these laws exist in the first place. In his characteristic way, he once remarked, "What breathes fire into the equations and makes a universe for them to describe?" As we approach the conclusion of a brief history of time, we must reflect on the significance of these ideas. Whether or not we believe the universe needs a creator, the progress of modern physics has allowed us to explore questions that were once thought to be purely metaphysical. The boundary between science and philosophy continues to blur, pushing the limits of what we can know. In the final part, we will explore Hawking's reflections on the future of science, the quest for knowledge, and the ultimate fate of the universe. If we do one day uncover the deepest laws of nature, what will that mean for humanity? Will we ever reach the final answers, or will the search for understanding go on forever? As we reach the final chapter of a brief history of time, we must reflect on the vast and intricate journey we have taken. Stephen Hawking has led us through the mysteries of black holes, the nature of time, the origins of the universe, and the ultimate quest for a theory of everything. But as we stand at the frontier of human knowledge, we must ask, will we ever reach the end of this journey? Will science ever discover a complete and final answer to all the questions we have? Hawking believed that we are getting closer to uncovering the fundamental laws that govern the universe. The progress made in theoretical physics over the last century, from Einstein's general relativity to the development of quantum mechanics, has transformed our understanding of space, time, and matter. Scientists have unified 3 of the 4 fundamental forces in the standard model of particle physics, and many believe that the remaining challenge is to incorporate gravity into this framework. If a quantum theory of gravity is discovered, it could lead to what is often called the theory of everything, a single set of equations that fully describes the workings of the cosmos. Yet, even if we achieve this goal, would it truly be the end of science? Would we, at last, know everything there is to know about the universe? Hawking remained both optimistic and cautious. On one hand, he believed that within a few decades, physicists might develop a working theory of quantum gravity, perhaps through string theory or some other approach. Such a discovery would be a monumental achievement, allowing us to understand the behavior of the universe at the smallest scales and at the most extreme conditions, such as inside black holes or at the moment of the Big Bang. But even if we reach this stage, Hawking acknowledged that a final theory of physics would not necessarily mean the end of discovery. Understanding the fundamental laws of nature is one thing, applying them to explain the vast complexities of the universe is another. The laws of physics may be simple, but their consequences, ranging from the formation of galaxies to the emergence of life, are anything but. For instance, even if we find a unified theory that describes how the universe works, it would not immediately explain why our particular universe has the properties it does. Why do the fundamental constants of nature, such as the strength of gravity or the charge of the electron, have the values they do? Are these values determined by deep mathematical necessity, or are they mere accidents of cosmic history? If the multiverse hypothesis is correct, then our universe may simply be one of an infinite number of possible universes, each with different physical laws. Furthermore, the discovery of a final theory would not answer deeper philosophical questions about existence. Why is there something rather than nothing? Why do the laws of physics exist at all? Even if we had a perfect set of equations describing the universe, the equations themselves do not explain why they are there or why the universe follows them. In this sense, the ultimate question of existence may always remain beyond the reach of science. Hawking also reflected on the future of humanity. If we are to continue our journey of discovery, we must survive long enough to do so. He warned that our species faces numerous existential risks: nuclear war, climate change, pandemics, and even threats from artificial intelligence. But perhaps the greatest challenge is the long-term survival of humanity itself. In his later years, Hawking became a strong advocate for space exploration. He argued that if humanity wishes to survive in the distant future, we must not remain confined to Earth. The planet is vulnerable to natural disasters and human-caused catastrophes, and at some point, whether in hundreds, thousands, or millions of years, it will become uninhabitable. If we want our species to endure, we must become a multi-planetary civilization. Colonizing other planets and eventually other star systems may be the only way to ensure the long-term survival of intelligent life. Hawking's work also touched on the nature of intelligence itself. As artificial intelligence, AI, advances, will machines surpass human intelligence? Could AI one day develop its own understanding of the universe, making human scientists obsolete? Or will AI serve as a tool that helps us push the boundaries of knowledge even further? Hawking was both excited and concerned about AI, warning that, if not controlled properly, it could become a threat to humanity. But if used wisely, it could help us solve some of the greatest mysteries of the cosmos. As a brief history of time draws to a close, Hawking leaves us with a sense of wonder and possibility. He reminds us that while we have made incredible progress in understanding the universe, there is still so much left to discover. Science is an ongoing process, not a finished book. The search for knowledge is what defines us as a species, and it is a journey that will continue for generations to come. One of Hawking's most famous quotes captures this spirit of curiosity and exploration. Remember to look up at the stars and not down at your feet. Try to make sense of what you see and wonder about what makes the universe exist. Be curious, and however difficult life may seem, there is always something you can do and succeed at. It matters that you don't just give up. And so, the journey continues, not just for physicists, but for all of us. The universe is vast, mysterious, and beautiful. Even if we do not yet have all the answers, the act of seeking them is what makes us truly human. The final question remains: if we do one day discover a complete and final theory of physics, will we have reached the end of knowledge? Or will we simply uncover deeper mysteries that we never even imagined? Perhaps, as Hawking believed, the true beauty of the universe lies not just in its laws, but in our endless pursuit to understand them. As we reach the end of a brief history of time, we step back to appreciate the incredible journey Stephen Hawking has taken us on. From the earliest human questions about the nature of existence to the cutting-edge discoveries of modern physics, we have explored the universe at every scale, delving into black holes, the fabric of space-time, quantum mechanics, and the origins of the cosmos itself. But what makes a brief history of time truly remarkable is not just its scientific content, it is its ability to inspire curiosity and wonder. Hawking had a rare gift, the ability to take some of the most complex ideas in physics and present them in a way that makes us feel like we are part of the grand adventure of discovery. He wrote not just for scientists, but for everyone who has ever looked up at the stars and asked, why? Throughout the book, one theme remains constant. The universe is governed by laws, and we are capable of understanding them. The idea that everything, from the motion of galaxies to the behavior of subatomic particles, follows precise mathematical principles is one of the greatest triumphs of human thought. And yet, as much as we have learned, Hawking reminds us that there is still much we do not know. The search for a theory of everything continues, and with it, the possibility that new and even deeper mysteries will be revealed. One of the most thought-provoking ideas Hawking leaves us with is the question of whether we will ever reach the final answers. If we do discover a complete theory of physics, what then? Will it mean the end of human curiosity, or will it open the door to even greater questions? The journey of science, as Hawking sees it, is an ever-expanding frontier, one that will continue as long as there are minds willing to explore it. But Hawking's work is not just about science, it is about human resilience. His own life was a testament to the power of determination, intellect, and curiosity. Diagnosed with ALS at the age of 21 and given only a few years to live, he defied all expectations, continuing to work, think, and inspire for more than 5 decades. His achievements were not just in the realm of theoretical physics. They were in proving that the pursuit of knowledge has no limits, not of the body, nor of the mind. His words encourage us not to take the universe for granted. Science is not something separate from us. It is a fundamental part of who we are. Every breakthrough, every question answered, and every new mystery discovered is a step forward in the endless quest to understand our place in the cosmos. Perhaps the most fitting way to conclude this journey is with Hawking's own words that remind us that the universe is not just something to be studied, but something to be experienced, wondered at, and explored. If we find the answer to that, it would be the ultimate triumph of human reason, for then we would truly know the mind of God.